problem that I handed out yesterday, the solution to it. And so as you recall, the problem as handed out yesterday was for the requirements, design requirements for a conventional distilling column, dripping and concentrating section in order to handle a feed rate of 15,000 gallons per hour, 7% alcohol, preheated 140 degrees Fahrenheit. With the specification that the heads cuts be taken from the condenser at the rate of about 60 gallons per hour. This is a rather arbitrary figure, but it's also realistic. And neutral brandy to be withdrawn to the side stream at 189 proof. And the reflux ratio is the internal, or the ratio of the liquid rate to the vapor rate of the concentrating section below the side stream is to be 0.80, and that is the region of the column where the reflux ratio is most important. Which would be equivalent to an external reflux ratio of 4.0 to 1 if all the product were withdrawn from the condenser. So we assume the allowable loss in the distillage is 400 volume percent alcohol and open streams to be used. So the first part of the problem is to estimate how many ideal stages or plates are required in the two sections, and how many are used for the aldehyde concentrating, or what's sometimes called the pasteurizing section, the number of plates between the side draw and the top of the column. And then there's some other questions which we'll come back to in a moment. Well, now this problem is somewhat more complicated than any we've had, but still it's a relatively simple problem as distillation design would go, because it's a single column and there's only two products plus the bottoms, and but anyway, it will illustrate how you would proceed in this, even for more complex problems, I hope. So the first thing to do in a case like that is, in a problem like this, is draw a little sketch so it's easy to visualize the process, which is done here at the top of this page. And then to make a listing of the explicit data, the stated requirements. And so I've constructed a little table here which includes that, plus a certain amount of implicit data, that which you'd have to work with, in order to obtain the flow rates in moles per hour, pound moles per hour. So there's a list of the various streams that we're interested in here: feed, heads, brandy, bottoms product, the vapor rate in the concentrating section, V sub n, the liquid overflow rate in the upper part of the concentrating section, which we call L sub n, and the liquid overflow rate below the draw-off point, L sub p. I've used the symbol L sub p, which of course is going to be lower than L sub n by the amount of the side stream product taken out as a boiling liquid. And then L sub m is the liquid overflow rate in the dripping section, and V sub m the vapor rate, and S represents the steam rate. So in other words, we use our old technique of proceeding to calculate by application of material balance equations. And so the first thing here, we write an alcohol mass balance on a mole basis. So we know from the table of implicit data up above here, we've calculated, well, I might go back to that. The feed rate is 7% by volume, which is 5.61% by weight, which is 2.27% mole basis. And using the conversion tables that we've been using. You can find that the average molecular weight is about 18.61 pounds per pound mole for that feed composition, assuming, of course, that it's water and alcohol. 15,000 gallons per hour, using the density for, well, I don't know where I shown that or not. Anyway, 15,000 gallons per hour times 8.34 times the specific gravity would give the gallons per hour, which is, no, well, the gallons per hour is specified, would give pounds per hour. I don't see quite where I put down the density of the feed rate here, but anyway, it came out to be 124,600 pounds per hour, which is equivalent to 7,600 moles per hour. So now, and similarly, the heads rate could be converted over to moles per hour. It comes out to be about 9.55. And so we don't know. We have to calculate what the Brandy rate is, the P rate, and also the bottoms rate we don't know. So those appear as unknowns in our mass balance there on the lower part of page 1. So the feed times the concentration of alcohol plus the steam multiplied by 0, because there's no alcohol in that, is equal to the heads rate times its concentration plus the product times its concentration, and the concentration is 0.1824 mole fraction, but the product rate P is an unknown. And the bottoms rate is also an unknown, although the concentration in mole percent is 0.30124 mole fraction. Anyway, you can solve this equation out and find that you have an equation and two unknowns, P and V. Now, at the present time, we have no other relationship that we can utilize to eliminate the B and the P terms. But we can make a reasonable estimate. So that's what I said we frequently do in the industrial type problems. We make some reasonable estimate and then go ahead and work a problem and then check back to see if the estimate was reasonable after we got the result. Well, that's what we've done here. It's fairly obvious that it wouldn't probably make much difference if you neglected the bottoms rate entirely with respect to the alcohol balance, because the alcohol content is so low. But maybe it's slightly more realistic to say that the amount of, to assume that the bottoms rate is approximately equal to the feed rate. In other words, the amount of product taken off the top is approximately going to be the same volume as the amount of steam that's introduced into the system in terms of volume, or in terms of mass, rather. That's the assumption we're making here anyway. So making that assumption, that the the bottom rate is equal to feed rate, then the amount of alcohol in the bottoms would be 0.83 moles of alcohol per hour. So you put that in and then solve for P, or the side stream product rate, then would come out to be 176 moles per hour. So you see that the amount of alcohol assumed here in the bottoms rate is less than 1% of the, well, it's about only about 0.5% of the amount in the product with that assumption. But now with that fact, we can plug those figures back in the table here and see what else we need to calculate. We need to calculate almost everything in the final column, mole rate per hour. So page 2 shows how you proceed to do that. The specified reflux ratio below the point of draw-off was, which we said was which is which is L over P, but using the proper symbols, it'd be L sub P over V sub N equal 8/10. And the relationship there is, of course, that L sub N, or the overflow rate above the draw-off product, is equal to the rate of the product draw-off, which is a boiling liquid or saturated liquid, plus the rate overflowing onto the section below, or L sub P rate. So solving that with the overall relationship that V sub N, or the vapor rate leaving the top of the column, is equal to the distillate rate plus the overflow rate back to the top of the column. Well, we can calculate the V sub N rate there. It comes out to be about 928 pound-moles per hour. And from that, it's simple enough to get the overflow rate at the top of the column, L sub N, by subtracting the D from that, which was 9.6, coming out with a figure of 918.4 moles per hour. So you can see now that the reflux ratio in the top part of the column is going to be 918 divided by 928, or almost 100%, and almost total reflux. It's actually about 0.99 would be the ratio, you see. Then we can calculate the side stream rate, L sub P, by subtracting P from the L sub N rate, because we're simply drawing off the product as a side stream liquid, reducing the liquid overflow at that tray by the amount diverted out to the side, and so that comes out to be 742. So now we've got most of the, we've got the all the vapor and liquid rates in the upper part of the column, or in other words, in the stripping section. Using the technique of applying and calculating the Q-line slope, we really don't need to know what the vapor rate and liquid rates are in the stripping section for the purpose of getting the number of plates. Although later on you'll see why we put those last three figures in there on the on that table on page 1. But for this part of the calculation, you don't need to know those. So we estimate Q by the technique we've used before for a 7% by volume ethyl alcohol water solution. And converting it over weight percent and using a table, which I think I gave a copy of from the Commercial Solvents Manual on Alcohol, you can find that the sensible heat of the feed is about 102 BTUs per pound. And the sensible heat of the feed at the boiling point, or at the saturation temperature, would be 168 BTUs per pound. And the heat of vaporization for alcohol water solution of this composition would be about 1,111 BTUs per pound. So the heat of vapor, the heat of the vapor would be that. Enthalpy of the vapor, I meant 1,1101. 1,101. So the heat of vaporization is the difference, or in other words, 943 BTUs per pound. Now we could have converted these figures over to pound to BTUs per pound mole, but if we're making the assumption that we're introducing the feed at a tray in the column where the composition is the liquid is essentially the same, well, then the composition would have to stay as the same at the point of feed entry. So if you convert it to pound, so if you convert it over to pound moles, the ratios of the feed rate to the vapor rate attacking it would be the same. So you really don't have to convert over, although it's not wrong if you do, to a pound mole basis. So you can just use the enthalpy on a pound basis. So that's what I've done here. And so the moles of vapor condensed at the feed plate to raise the feed, 1 mole of feed to the boiling point, is the same ratio as the amount of heat required to raise a pound mole of vapor per pound of mole of feed. So in other words, the Q term then is equal to 1 plus the amount of vapor condensed to heat up that 1 pound or 1 of a feed to the boiling point, which is, you have to supply 168 BTUs less 102, or 66 BTUs per pound to get it up to the boiling point. And that's going to be satisfied by condensing vapor, which has a heat of vapor content of 943 BTUs per pound. So Q then comes out to be 1 plus 0.0698. So the slope of the Q line of Q over Q minus 1 would be 15.4 to 1. As I already suggested here, the slope of the operating line in the concentrating section above the side stream, or near the top, is 918 over 928, or 0.990. The slope of the operating below the P plate, we can use here a check of our figures. 742.4 divided by 928 is equal to 0.80 as specified, previously specified. So now we have sufficient information to construct the McCabe-Thiele diagram. So I'll pass out now copy this, which we can look at. Did everybody get a copy of this solution? Would you pass that back, please? I'm sort of anchored here on a leash. Unfortunately, the steps that I had drawn on here in the lower part of the diagram didn't show up very well, but I think you can make out where they were. So, using our usual procedure, we've located on the on the chart here the composition of the top distillate, which is 0.856 mole fraction, the side stream product, which is about 0.81 mole fraction, and of course bottoms is so low that's impossible to locate it on the main chart. So I've attempted to do it on this little expanded chart, and it's still also so small that it's not very realistically solved by this kind of a graph. So we've drawn the operating line now from the x sub d of 0.856. As near as we can tell, near as we can draw it, a slope of 0.99 is essentially the right on the diagonal. So you can't see you can't tell the difference between that and the diagonal. So for this little stretch here, the operating line is for all practical purposes, is the same as the diagonal. And so it takes 1, 2, 3, about 4 steps, or 4 ideal plates to drop down from 192 proof to 189 proof under essentially total reflux. Now at that point, the operating line changes slope to correspond to the new liquid vapor ratio rate, which is 0.80 to 1. If you had a little bit more, of a, let's say this is part of this. Let's say this is definitely part of this thing here. Here would be the curve. And let's say we had, this is the top distillate. And when exaggerated, we had a side stream composition where there was an appreciable amount of top product taken off. So we had a significantly representable slope, such as indicated here. And then at this point, we change the slope by taking out more of a liquid side stream. Why then, at that point, the slope changes. Or in other words, the two operating lines, the slopes of the two separate operating lines, if you want to consider it as two separate operating lines, intersect at the side stream composition. So that's what we've done here, but it's not so obvious that this is, well, this is a slope of 0.99. It doesn't show up as being separate from the diagonal. So we continue on down. I'm taking our stepwise steps. And, well, first of all, we've plotted in the Q line, of course. We can plot X sub F down there in the lower left-hand corner on the main chart. And the slope of the Q line of 15.4 to 1 makes it just slightly inclined to the right from the vertical. And now we continue to take the steps along, and although the steps, the lines here become not very clear, or they almost disappeared. If you look along, you'll see that in parentheses the number of the ideal step written below there, so you can barely see the outlines of the steps drawn in. So it looks like we required a total of about 13 plus a slight bit more, just slightly more than 13, to span the change in liquid composition down to X sub F, or down to intersection of the Q line with the operating line. So over on the right-hand side then of this chart, I've written here the number of ideal plates in the concentrating section. Above the side stream is essentially 4, and below the side stream it's 9 plus a fraction, or about 13 plus. Then locating the conditions for the stripping section on this little side chart here. The way I do that is to locate of course, the Q line, draw the Q line in, and then you draw in a little bit of the lower part of the operating line for the rectifying section in order to find the point of intersection. Or another way to do it is just simply try to translate this point of intersection over here of the Q line and the operating line in the concentrating section, and read off the points and relocate it. So then we can draw the operating line in the stripping section from the point of intersection of the Q line and the rectifying section line down to X sub B on the x-axis of 0.00124. Well, this is a little bit indefinite there as to the way that, but anyway, it's essentially where I've got it there. So it appears that you need about a total of 20 steps to get down to this specified bottoms concentration. So that's the answer to the first part of the requirement, as I got it. I didn't bring in here with me, but I did solve this same part of the problem here by replotting on what we call probability paper, logarithmic paper on both scales. I'll bring you an example of that when I get a chance. Where you plot the operating line and the equilibrium curve. In that case, the equilibrium curve down the lower end becomes a straight line, and the operating line becomes a slight curve. But at least it gives you a lot of space to work, and so you can do it more accurately. There's a little illustration of that here in this textbook by Brown, and perhaps I can find it and show it to you here. Let's see. Right. Just a moment. I know it's a little too far away to see, but on page 370 of this book, here's a plot of the mole fraction of ethanol in the liquid on a logarithmic basis, and in the vapor on a logarithmic basis. And so you can see, perhaps you can't see, but I point out that the upper line is the equilibrium line, and it's essentially a straight line. And the excuse me, maybe I didn't say that right. The upper line is the equilibrium curve, and it's a straight line. Because down this very low region, we're essentially dealing with Henry's law that y is equal to kx. In other words, it's about 10.8 to 1, the k constant, in this very low region of alcohol concentration. Then the operating line, plotted on a log scale, becomes slightly curved. But you see, it enables the steps to remain essentially the same size when you're taking the stepwise there, and so you can read them all quite accurately. And I'll do that. I've done that for this particular case, but I didn't bring in the solution with me. Well, now, are there any questions about this particular thing? Yes, it's the bottom part of the stripping section. Or you can use it perhaps for the whole stripping section in this case. Yeah.
Yeah, throughout here in the header, I've noticed you've got mole percent or mole fraction for the bottoms. It's 0.124, the mole percentage. The mole fraction you have down there is 0.00124. I think you have 120 zeros for the mole fraction of the bottoms.
Yeah.
I don't know if that makes a difference at all. Just trying to tell you.
Let's see now, where's this now? The
mole fraction of the bottoms. You have 3 zeros, you should only have 2.
On your this one.
And it's throughout the handout too. If it makes a difference.
And what was it supposed to be?
Just 2 zeros.
0.00.
There is a decimal error there of one point, and I don't know which one. I think that in the table back there on page 1 is where the error is. It looks like that should be 0.0124. Because mole percent is always less than weight percent. I'm almost certain that was a typographical error, and I hadn't noticed it before after several years here. And that is a percent basis, so if that's 0.0124%, well, then the mole fraction would be 30124 as I have it on the chart. So I think the solution is correct. All right. Well, the next question that was asked here is at what plate, which ideal plate would you connect the fusel oil decanter? Well, we haven't talked about that part yet, but suffice to say that, as indicated on the top of page 3 of the solution, that you can consider that fusel oil concentrates at the plate which is closest to about 135 proof. Or I would say perhaps sometimes I might say 130 proof, but somewhere between 130 and 135, if there is a tray that has that concentration, will have the maximum concentration of amyl alcohol on it. Perhaps the butyl and the propyl alcohol would be one tray above it. But from a very practical sense, if you can find a tray that has an indicated proof of around 130 to 135, that'll be the plate where you'll have about the maximum concentration, and of course that's where you'd want to connect the draw-off point if you're trying to separate it. So now, referring back to the diagram, well, translating that into a mole, it comes out to be about 37 mole percent. So referring back to the diagram now, and this mole percent would be attained between the 11th and 12th plates from the top. And so if we translated this, and if we had some plate efficiency factor to apply, which we have stated here as 0.8 tenths, well, I didn't work that out, but it'd be, let's say if you wanted to say 11.5 divided by 8 tenths, it'd be, how much would that be? About 14th tray or something like that. In a later period, I'll take up a little bit more about this principles of fusel oil separation and decantation. Was there any question about it up to now? Well, the next requirement then was if the average plate efficiency of the rectifying section is 80%, what would be the temperature in degrees Fahrenheit on actual plates 1, 5, and 10 numbered from the top? Well, if you put down actual plate number here as done there on part C, 1, 5, and 10, the equivalent ideal plate number would be 8 tenths, 4, and 8. So you read off from your chart the mole percent of the liquid alcohol at those particular levels in the column, and then you refer to the equilibrium data sheet or boiling point composition diagram, and neglecting column pressure, read off that the temperatures are all around about 173. That wasn't a very illustrative problem, because this is all in the upper part of the column where the temperature change is very small. All right, what's the minimum reflux ratio? Well, now we have to go back to the chart for that. And you'll see that we've drawn in a dotted line here, which, because the feed is at such low concentration, the minimum reflux ratio is determined by the minimum slope of that line, which would satisfy the requirement of extending the operating line clear down to the intersection with the Q line. Because the feed concentration is so low, there's no chance, no opportunity for that for this minimum reflux slope line to be established by the tangential point with the curve. So, reading off graphically that slope by scaling off of the scale, I determined that the reflux ratio, L sub P over V, or the slope of that line, is about 0.650 to 1. Now that is the only meaningful ratio that we got here, but in parentheses I've calculated that this would be an equivalent to an overhead product external reflux ratio of about 1.86 to 1. But there's no point under a situation like this where there's any reflux ratio that you can measure 1.86 to 1, because it just because of the side stream method of product removal. Let's see, the next part was there's some other questions there we haven't really talked about before. Part E was, what is the total height and diameter of each section if the plate spacing of 12 inches is chosen for the rectifying section and 15 inches in the stripping section? Well, that, of course, is specifying a rather obvious parameter, and but it is more or less realistic that the allowable vapor velocity for the 12-inch spacing would be appropriately about 2 feet per second, And for the stripping section, might permit a velocity of about 4 feet per second. So in other words, we'd have, very simply, if we have 14 ideal plates required in the rectifying section, I think before we said 13 plus, wasn't it? Or about 14 ideal plates. And assuming an average overall composition of an efficiency of 8/10 or 80%, comes out to be 17 or 18 actual plates. And of course the height then would be, if we have 12-inch plate spacing, would be simply 1 foot per plate, or in other words 18 feet. And the diameter now, this is something else. This is something that we want to consider that we haven't had before. If the vapor velocity is 2 feet per second, what size diameter do we have to permit this vapor velocity? Well, the easiest way to do that is to work again on a pound-mole basis, and we've already indicated that the vapor rate through this section is 928 pound-moles per hour. Well, 1 pound-mole of a gas occupies 359 cubic feet at standard temperature and pressure, or namely 32 degrees Fahrenheit and 1 atmosphere pressure. Now, if we assume that the pressure change is negligible, but that the volume is that occupied is that which we would calculate assuming a perfect gas, which I said is a reasonable assumption at low pressures like atmospheric pressure. Well, you simply have to multiply 928 pound-moles per hour by 359 cubic feet per pound-mole times the ratio of the absolute temperatures. The absolute temperature on a Fahrenheit scale is degrees Fahrenheit. On the absolute scale, using the Fahrenheit scale, or degrees ranking as it's called, is equal to degrees Fahrenheit plus 460. In other words, 32 degrees Fahrenheit is 460 degrees ranking. That's the same as if you're using the centigrade or the Celsius scale. You'd say that the absolute degrees Celsius is equal to degrees centigrade plus 273. 460 is the corresponding term. So you multiply by the ratio of the temperatures. Well, I had to look up. Actually, the temperature varies somewhat through the column, but I took the temperature which would exist at the highest temperature which would exist, which would be down near the feed tray, down near the bottom. And if you look up in a table, you'll find that would be about 190 degrees Fahrenheit. The boiling point of about 7% alcohol, I imagine, that was at the feed rate, the concentration down near the bottom. Anyway, the result comes out to be 122 cubic feet per second. The overall volume rate of the vapor. The top of page 4. It's not the boiling point. It'd be the boiling point of the feed, 109 degrees Fahrenheit, or the saturation temperature.
But you have on another page that's 203 degrees.
I do.
Page number 2, page 7. And up.
Well, let's see. I don't know where it's.
Am I interpreting it wrong? That's what I want to know.
Well, let me see now. What is the answer to that? Well, I'm not sure whether I was consistent in that or not, but let me explain. If we take the concentration of alcohol at the lowest plate here, which would be slightly greater concentration of alcohol because the Q line is inclined to the right. This may account for that much. I don't know if it would or not, but the fact now we're considering the vapor on the lowest tray would be a slightly higher alcohol concentration than the feed because of this effect of the Q line. I'm not sure that's the answer. It may be that I use some other basis to estimate the temperature and, that I don't remember now. But the net result wouldn't have very much effect anyway. If we had a 10-degree error, it wouldn't really have much effect on the result because these are pretty big estimates anyway. Guesstimates is a good word, the word using now.
Guesstimate?
Yeah. But anyway, it's they're reasonable estimates, I would think. I would say. But because this is a ratio of absolute temperatures here, as far as the a 10-degree difference there in the boiling point of the actual degrees Fahrenheit of the vapor wouldn't have very much effect on the vapor rate. You don't believe me? You understand what I meant? Yeah, I think you do. Well, anyway, if we say then that this is the using the symbol capital V for the volumetric vapor rate, this is equal to the linear velocity, small v, times the cross-sectional area in square feet. You see, if you multiply square feet by feet per second, you get cubic feet per second, which is what the vapor rate is expressed in. And of course, the cross-sectional area in its simplest form is pi d squared over 4, so you're substituting the values in, solve for d, comes out to be about 8.8 feet diameter of the rectifying section. And that's quite reasonable. There aren't many columns in California that have that diameter, maybe only one. But there also aren't many that take 15,000 gallons per hour feed either, but there are one or two or three that do. There are several that are 6 feet in diameter that take about 10,000, from 8 to 10,000 gallons per hour feed, so this is in the ballpark. Now, to get the diameter of the stripping section, we need to calculate the vapor rate in that section. And so, we can say that first of all, that at the base, if we're using live steam, the vapor rate is, on a mole basis, is the steam rate, because that's what the initial vapor is at the base. No other source of vapor. But this is also equal to this has to be sufficient to provide the vapor rate in the upper section, V sub n, plus the amount that was condensed at the feed tray in order to bring the feed up to the saturation temperature, which is Q minus 1 times F. And so, substituting those values in here, we'll see that we have to add to 928, the vapor rate in the top part of the column, the rectifying section, the additional value of 468 moles of vapor. In other words, almost about 50% as much vapor was condensed at the feed tray as passes on up. 468 versus 928. And this is particularly the case in where you have very low alcohol feeds like this and have appreciable requirement of heating the feed up to the boiling point from 140 up to over 200. So the vapor rate then comes out to be around 1,396 according to these figures here, moles per hour. Well, so calculating the vapor rate here again is a little bit arbitrary in the sense that I assume the temperature of 212 degrees Fahrenheit at the base of the column. In reality, there is a back pressure which would raise the temperature to probably 4 or 5 degrees Fahrenheit, but it wouldn't have any major effect on the result, whether you take 212 or 216 or 218 degrees Fahrenheit. So again, converting that vapor rate of 1,396 moles per hour over to cubic feet per second, we come out with 193 cubic feet per second. So applying the same type of formulation to calculate the D, where the allowable vapor rate was 4 feet per second, linear rate, comes out to be 7.8 feet diameter. Well, that's slightly less than the diameter of the rectifying section as we calculated here. But anyway, it's still realistic. It's, in most cases, in California at least, the diameter of the two sections are the same. It's rare, however, that the rectifying section is larger, but then sometimes you can make a justification for that to have the rectifying section larger in diameter than the stripping section, as is here, as was done here. Well, let's see, that's the answer, that's the question, that was the answer to part E. Now, part F introduces some concepts that we really haven't had, but we'll go through it anyway. Calculate the area of the, well, I'm not going to have much time to do that. Calculate the area of the condenser tube surface for the defumator if it is to condense but not cool 90% of the vapor to a saturated liquid at the boiling point. And 10% of the vapor, of course, would go on over to the final condenser. And I've given you the fact that the latent heat of 192 proof alcohol vapor is about 404 BTUs per pound. And cooling water supplied at 73 degrees and discharged at 133 degrees. Well, this gets into the question of heat transfer considerations, and what we have to do there is to calculate the average mean temperature of heat transfer between the water and the vapor. And you see this little diagram shows the vapor goes in at 173 and of course leaves at a constant temperature of 173, but the water increases from 73 to 133 during the passage. So it turns out to be, in that case, we have to calculate what's called a log mean temperature difference. And I hope maybe I'll have time to go into that later for those of you not familiar with it. But anyway, it comes out to be about 65.5 degrees Fahrenheit. So now we have a general overall equation of heat transfer, which is not clearly stated there anywhere that I can see, but anyway, I'll write it down. It is that the Q is equal to the overall heat transfer coefficient times the mean temperature difference times the cross-sectional area. So in other words, we know what this is, and it was stated what we're going to assume the U value is, and we calculated delta M, so then we calculate A. So in other words, A is equal to Q divided by U times delta T sub M. And so I won't have time to go into that further, but that's the formula that we use to calculate this. Cross-sectional area about 1,735 square feet. That's a pretty big heat exchanger, and it's very possible that my statement of the overall heat transfer coefficient of 125 BTUs per hour per square foot per degree Fahrenheit is not not realistic. It sometimes is realistic, though, because you get fouling in the tubes and coating of the tubes, and then the heat transfer coefficient drops off significantly. So, well, you can read to the last part here. In other words, I just calculated this steam rate here from this in order to check on the previous assumption we made that the bottoms rate was about equal to the feed rate. Well, it turns out to be it's missed it by a fair amount, but it wouldn't be, it still would not have any significant effect on the calculations. Well, now in the laboratory today we're going to do some, have some tasting tests and experience with known solutions, although some of them will be unknown.